All right, well, I present to you Rhys Elsmore. Rhys is an internet mockup at Heroku based on the platform security team. The rest of some of his day usually consists of strong coffee and making up fake radio jingles about items in his kitchen. But let's give it up for Rhys.
How we doing? Yeah. So anyway, thank you. I'm Rhys. I'm on the security team at Heroku, and I make sure that our platform's not abused or broken into. So this is my talk. Basically, the concept is to just use Postgres and use something else when it stops working. Hint, I haven't found it to stop working for many of the use cases. So for this talk, I want you to bear with me. Normal heart rate 60, 70. Fitbit says 130 at the moment. You're guinea pigs for different sort of presenter notes to what I usually do. So if I have to go back some slides, or I stumble, or I stop, please bear with me. Making me a little bit nervous, but we'll get through it. So there's a repo. If you go there at the moment, it is empty. I've got about 10 IPython notebooks I'm going to be putting in there, and I want to turn it into a sort of, once a week, I take an issue, I turn it into an IPython notebook to solve an issue with Postgres. So this is what I'm going to be stepping through. Basically, the pain of many services, be it backing services or services that talk to each other. Going through from basically all in one part, just some real-world use cases of Postgres beyond your normal selects, group bys, ordering. Also going to be talking about some of the things you didn't know that Postgres could do. You can actually do listen, notify, and pub sub in your database. And I'm going to also cover things that you should make Postgres do. So I'm going to be talking about security vulnerabilities by the way of race conditions. So that should be kind of interesting. If you do application development and you've been sort of lured by the case of microservices, then you're going to understand this. I like to call it software-oriented architecture. Basically, it's just pain. Say you've got a layout like this, and you get a request from Flask. Basically, you're storing an order within a Postgres database, and then you're calling Celery to take that order out of Postgres and shove it into Redis to cache. Then you might shove it into Neo4j and then query Neo4j for a network of other people who have placed that orders and put that into Elasticsearch so that you might be able to search for similar people. Then you get a request for another order, and it looks in Redis, it doesn't find it, then it goes over to Postgres and says, well, it's not here, it must be in the MongoDB warehouse. Celery actually calls Hadoop, which puts data into Redshift and then shoves it into the MongoDB warehouse. Then Celery might query that occasionally and put it into Cassandra, and then an attacker over here accesses Cassandra because you've got an engineer who didn't consider, securing Cassandra. Then the CEO gets kind of mad because the data's taken out of Cassandra, his big data, and it's put onto Pastebin for everyone to see. Basically, it's a Ruby Goldberg effect. It's poor planning, you're not thinking the problem through, there's premature optimization, and this need to scale. I don't like that word. You might see something on Hacker News or Y Combinator about using the hippest piece of technology. And honestly, for each piece of technology you introduce into your stack, you're going to be putting burdens like this on your team. You've got more threat surface to secure. You've got problems when it comes to tracing bugs across multiple servers, and performance profiling. That's absolutely terrible. With this cost, if the shiny new tool you add drops your query time in half, but causes everything to basically go to crap, then what use is it? I went through this pain for 2 years trying to use shiny add-ons in the Heroku store. So this is my motto. This is where I am, and basically, as the lead engineer on a bunch of different security-focused projects over the last 2 years, the more I follow this advice, the better off the projects seem to run and the better off we are afterwards. So, this is anecdotal evidence from me, but I've been personally impressed by the results of just sticking to one data store. The key project that I wanted to cover was just this idea of unbounded datasets. So I'll go through the problem space. Basically, a crap load of data. It's coming in fast, it's requiring storage, and a little bit of analysis. So old me would have jumped and looked at solutions such as Hadoop or Spark or Cassandra. But we took a bit of time and we decided to go down the path of seeing if Postgres could actually handle this. So we started documenting our facts. Heroku apps restart a fair bit. You can issue a command to restart them, and after 24 hours, we generally restart them. And each app has more than one process, and each process lives on a different server. And we've got a lot of apps running at once, like hundreds of thousands. And each start and restop that occurs, we get this event from our orchestration team. So with these facts in mind, and this event that we're receiving looks a little bit like this, we decided to look at some more facts, and that's Heroku apps can live on any server. So we've got a lot of different variations of this event coming through. Rebalancing takes place often. These apps move multiple times a day. For anyone who hasn't used AWS, there are gremlins everywhere. Instances disappear, instances restart. The reason for storing this data, on the security team, we look at abuse reports, we look at intrusion detection, abuse detection, people's billing rates. And this old method that we had that was actually a database table maintained by the billing team, it was just causing 30-minute queries. There were timeouts, there were frustration. It was a single table with so many records that issuing a delete from wouldn't actually work because there were so many records. So with these assumptions in mind, we started looking at what we actually needed. And we don't actually care about the start events. We just really want to store when the dyno was stopped and a history of when it was run. And we actually only need 30 days of this hot storage. Afterwards, we can just move to S3. With our calculations, it looked like we were getting about 300 million records a month. And we wanted to be able to query them as little as possible and have this system that we didn't have to maintain a lot. Just need to sit there and run and do just that. So what we did, we just created a table like this. But with a little bit of difference, Postgres has this feature where you can actually inherit from a parent table and inherit the schema. There's a few gotchas where it won't inherit constraints or it only inherits indexes at create time. That causes a problem when you try and propagate a new index across many tables. But basically, this takes your data and it splits it up into small logical tables. It doesn't do this all by itself, though. I mean, selecting, you can select from dynos, and that will query every table for what you're looking for. You can delete from dynos. You can't delete from dynos, but you can drop a table. So with our time-stamped tables like this, removing history was just a matter of deleting a table. What I touched on, though, was insert into dynos was going to be hard. So what we did, we looked at the problem and we realized that we could just run a cron every 10 minutes to create some new partitions and remove any table that was 30 or 60 days old. And we also created a way to rewrite a trigger for any insert that was occurring to the dynos table. It would pass the created value, and it would rewrite the query to insert it into the actual proper child table. This script will be in the repo at the end of the talk. So every 10 minutes, we just ended up running the select message partitions query. And that would allow us to insert into a master table, it would get sent to a child table. And once we started looking at our indexes we used, so we had a few hard lessons along the way, but this is where we decided is optimal. We make use of the B-tree gist index. So what we can do, we can take a start time and an end time and add an attribute to it and query that really quickly. I'll go into some of the queries that we used, but for data of this size, we ended up using 7 indexes. So that's pretty good. I'll give you an example of some of the queries. So in the event that we receive an abuse report for an instance, so an IP address and a time, we could actually pull the running apps on that instance at that time. Now, if you look over here, the median runtime for 300 million rows is 4 milliseconds. That's pretty damn good. Now, you might pull 100 apps that were running on this instance at one time. We realized that if we got 2 abuse reports for the same matter, we could do 2 queries and intersect the rows and find the common app ID between both of them. And that would take about 8 milliseconds. So that's pretty good. With this sort of query, we could if we discovered that there was an app that was being malicious or trying to pop our infrastructure, we could actually pull a historic reference of where this app was at this certain time, what servers it was running on. That was actually 2 milliseconds. So that's pretty good. Now, 1800 milliseconds, it might not be good, but when we consider that what we're doing is picking every app that runs on Heroku and getting a sum of the hours that it's used on our platform over the past month, and it takes 1800 milliseconds, I can live with that. That's not much out of my day, and compared to running Elastic Hadoop on Amazon and trying to maintain that, I'd much rather be in this place. And the takeaways were that we got quicker queries. Most things run in a matter of seconds. it's maintainable. We've got monitoring set up. It hasn't gone off in 3 months. I haven't touched it. And we came into this with a lot of hesitations about this wanting to store all the data and having data as far back as we could go. I personally, and most of my teammates, haven't touched the cold storage. It's there in Amazon if we need it, but haven't touched it. And the cost is reasonable. This is all done on a Postgres instance with 15 gig of RAM, one server and a few processors talking to it. This was the project for me that really showed that, hey, Postgres does a pretty good job at the heavy lifting, and there's a lot of cool features. And from here, I actually started looking to other ways that we could use Postgres and supplement other services with this tool. So who uses code level locks in your DB? You've got multiple processes across multiple servers, and they need exclusive access to one thing. Anybody? Yeah, a few people. So do you use Redis or Memcache for that? Files? Yeah, okay. So, there's multiple ways to do it, and we used Redis for a long time, and, with this example, we've got a clock process, and what this does, it queries Braintree, and it pulls in a list of all card verifications that have happened. Due to the way we query Braintree, we've got to give it a start time and an end time, so what we do, we just give it the start time of the last record that we pulled in, and it pulls in every record since then. But to avoid any sort of race conditions, we needed to ensure that this ran only once, so we didn't want to miss out on any of the records being pulled in, so say we've got the setup like this and someone issues the clock equals 2, so they scale to 2 processes command. We wanted to prevent this and race conditions. So what we did, we put the Redis lock in. If clock 2 starts up, it tries to acquire the lock, but it can't get it. Now, what we decided was to actually scrap Redis in this case. Using Postgres, you can query for any sort of lock that you want. You can give it a 64-bit integer, so we just take a string, transform it into a number, and we've written our own tool around this to obtain locks, but there's many out there for Django and SQL Alchemy where you can just use Postgres instead of adding a moving part of Redis. Now, that's a pretty crude example. What really impressed me was social graphs. So if anyone's used something like Neo4j, where you can get directed graphs and transverse graphs and such, I never knew that Postgres could actually do this. So what we have here is basically a user ID, the credit card they've used, and the label. Were they a bad user? Have we labeled them as good, or are they unlabeled? Now, we started out creating a graph like this. Basically, we're taking a union of card to user and user to card. Basically, an undirected graph. Now, this is a small query, it's small text to fit it all in, but what I'm going to do is just step through it. So recursively, Postgres has a common table expression declaration called with recursive. So you can recursively select your initial rows and then recursively go through those. So what we're doing, we're recursively getting all the bad users. We're linking them with other cards and users who have not been labeled bad, except where we form a loop. And from this set, we're finding all end nodes who are users. And what that gives us, now this text is very small as well. I've got an example here, but basically, it steps through how a user is related to a card to a user. It just gives us a graph of how it transverses. And what this actually enables us to do is to look at user A, so someone we've found who used a stolen credit card. They might have used card A, but then user B, who is not bad, they've also used that card. And they've used card B, and user C, who is not bad, they might be unlabeled, they've also used that card B. That's pretty cool in Postgres in about 67 lines of code. My initial thoughts would have been to put this data into Neo4j and set up a syncing mechanism. I'm lazy. I'm lazy at work. I'm trying to be less lazy outside of work, but I want to spend my 8 hours a day being productive. And with the amount of data, it just seemed like an absolute nightmare. So keeping it in Postgres has been really effective. Basically, we're able to transverse graphs like this, and using this with recursive method, you can actually implement some well-known tools that other companies have used. So user A and user B share common connections. User A is connected to user E through these users, or the you might know feature. I won't explain that because I'm just going to get tongue-tied. So how many people didn't know that you could do social graphs like that in Postgres? Pretty cool feature? Yeah. I won't cover this too much because I didn't have many really good examples that I could share that actually gave us anything interesting. So what I did, I took the same sort of data where we have a user ID, a card ID, and a verified at, and I basically ran it through this window partition function, basically some context within each row of your query. So this is actually in one of the IPython notebooks. If you see here, basically I've got all these keywords like partition and lag and unbounded preceding and current row. Basically, you're able to look at each row and get some statistics about the row before it and the row after it based on some common groupings. So in this case, I've taken the user ID and I'm able to see that this user first verified 194 days ago. Their last verification before this one was 2 days and 1 hour and 54 minutes ago, and this is number 57 of their verification. I'll explain that. That's user ID, that's their first verification, that's their most previous, and that's how many previous verifications the user had done at this point. Before investigating these functions, I always thought that I would have to do subqueries and pull this data out and munge it in Python and put it back together. It's not the case. I can do that within the actual database. That was a pretty cool epiphany, and I've been exploring those more, and we use those in data collection to drive some of our models. So, like I said, I wouldn't touch on that too much, but I will touch on common table expressions a bit more. These blew my mind. Basically, these statements are referred to as common table expressions, or CTEs, if you see them on people talking about them, and think about them as just defining these temporary tables that exist for just one query. So here I'm declaring with stats as, and I'm basically running the same query as last time, and then I'm able to select from that stats table, or CTE that I just declared, within the same query. I don't have to create temporary tables or subselects or anything like that. I'm just able to query from another temporary table I've created. One cool feature we do use CTEs for is basically taking all of our users who have been deleted and moving them into an archived users table. That begin isolation level serializable. I'll talk about that with the racing editions at the end. But basically, within a few lines of code, we're able to move all of our deleted users into an archived table. Yeah, it's really easy. We can also query them with a CTE. So we say all users is basically the union of users and our archive users, and we can query them the same way. I always thought temporary tables were the thing, but yeah, this has really blown my mind. Notify listen. I know a few talks have touched on this, so I didn't add too much about it. Basically, within a Postgres shell, you can say listen on a queue. Now, if you issue this within the PSQL terminal, it'll go into asynchronous mode. Another process, or from within the same terminal, you can say notify queue of value. That's just what I've used. And basically, that message is received. Now, on its own like that, it's really boring. But for example, you can, whenever you update a row, you can notify a certain queue that that row has been updated and have a Python process listening to that queue in order to, maybe clear a Redis cache or update an external data store. Now, I talked about service pane, but that's something you might want to do. It's also an alternative to signals and keeping them within the database. One dragon, though, is that the messages are not persistent. So what I have seen some people do is use a trigger to put a notification into an updates table and then notify it when an insert occurs on that updates table. And also the service consuming those notifications is also able to query that updates table in case they miss something. Now, like I said, I'm lazy, and when it comes to database schemas, I'm really vain. I always get hesitant about putting things in the wrong order or making things look ugly. I mean, I want the ID row to be the first row in there. So bear with me while I explain this one. Say we've got a table which is base users, and we've got a name and is awesome. And we can see that is awesome defaults to true, and we've inserted these people that are obviously awesome. If we alter that table, Postgres doesn't actually allow us to specify where we want the row. So I've added a primary key here, and if I look at the schema again, that row, that new column is put on the end. That doesn't look cool. If I go in to inspect the schema and I see that, I don't know, something clicks in my head, but updatable views actually solve this problem, which most people would say is kind of silly. What you can do, you can create a view. So I've created a view called public users, and I've put it in the order that I actually want, and now I can select from it. Okay, that's pretty cool for a view. These things are in most database systems. If I have a look at it, it's in the order I want. But with Postgres, if you issue an update to that view, it will actually proxy that to the table which the view is based on. So that was something that really blew my mind, and yeah, it's got a few gotchas when you're using multiple tables and you're doing aggregates and such. But this gave us a way to not worry about the schema because ideally we do want the schema to be in some sort of order. Foreign data wrappers is something I've been using a fair bit with our microservices exploration. Basically, this is database 1, so I've created a table called users, and I insert some values into that table. Over on database 2, I enable my Postgres foreign data wrapper. I create a server called the remote DB, and there's a user mapping in there, and I create a foreign table called remote users. What you can do on the DB2 side is then select from those remote users, and across the network, it will pull them in using Postgres queries. This just doesn't stop at selecting, though. You can also do updates, deletes work, you can do inserts. So that was something that was completely new to me before I embarked on this adventure. So I touched on this within my JavaScript talk yesterday, but Postgres has a fair few wrappers. I looked last night at the latest list, and there's things like Heroku data clips, there's things like RSS, you can do HTTP queries. Most of these things are enabled by 2 or 3 commands, or you need to download something and build it, but when you've got ways to talk to Docker and OS query and OpenStack from within your database, it makes things pretty interesting. It turns your data store into something that's a bit more extensible. Has anyone used Materialized Views? Okay, a few people. Say I have a table called users, and I insert some people into that user tables, and I do a one-to-many association of the user and their cats. So as you can see over here, Jane has Mittens, and Bridget has Ragnar the Great and Almighty. That's her cat. I can actually say create Materialized View, which is user cat counts, and I can create an index on it, and that becomes a persisted view of that data. I can select from it. I can't actually insert into it, but say crazy cat Rhys puts his cats in there. If I try and select from it, you'll see that it's not there. What I actually have to do is say refresh Materialized View, user cat counts. I try and select it from there again, and I've actually got the wrong result. That's not a function of Postgres, that's my poor slide. So excuse me, there should be 7 cats. But Materialized Views, what I personally use them for, I use them for importing from other Postgres tables. So we might have a team over here who's got a list of users and some sort of attribute. I'll periodically pull them in with a cron. We also do roll-ups of data that doesn't need to be that fresh, and also add some caching into the database. So it's basically caching a query. As of Postgres 9.4, you can't actually refresh them concurrently without you can refresh them concurrently without blocking other queries. But if you do issue a refresh, it's got to go through everything again and do it from scratch. We might see partial refreshes in the future, and that would be really exciting. One question I put to is, can you use a trigger to refresh a Materialized View? And that's actually the case. For our payment verifications, we use multiple triggers to refresh Materialized Views of rolled up stats of how users are verified. So one thing that was also kind of exciting is that Postgres has range types. So say we've got a table called cat reservations, and you can reserve a cat for a period of time, probably for padding or such. You can see here I've reserved Mr. Mittens from 2 p.m. to 1500. If I save that and then I try and reserve again, I get a conflicting key value because there's an exclusion constraint. Basically, it's not letting me go within that same period as the first cat was reserved. You can see here I've used a square bracket and a normal bracket on different ends. They're upper bound and lower bound inclusion and exclusion constraints. So I can say, it's basically less than or greater to, greater than, you know what I mean. Now this is where I didn't take notes, so it starts to get kind of curly here, and this is the new part I was talking about. JSON in Postgres. This was exciting because we were able to do away with our schemaless MongoDB setup. Once again with the cats, sorry, I had a common pattern here. I can create a table called cats, and I've got a column called metadata, and that's defined as the JSON B data type. Postgres 9.3 has JSON. This is JSON binary, so it doesn't just store a validated textual representation of the JSON blob. It actually parses it and does some intelligent things with it. So you can see here that I put in 3 cats, and their likes, their hates, because we all know cats hate most things. Now, if I do a select from cats, you can see that it returns the textual representation, which was the first column, and then it returns the metadata, and it's basically a JSON blob. what I can do is query that. So I can say, well, where does the metadata contain the object where I've got a key of like, and it's an array with nihilism in there? And I get a result like this. So that's pretty cool. You can query JSON. What if I was to use one of the JSON-B operators where it takes every array element and turns it into an actual row? You can see here I've got the cat, I've got its like, and its hate. This is a really, really simple query, but it's pretty powerful. We use it to, one of the things we do is store a file list of just file names and MD5 hashes of some of the code that's pushed to us. We were storing that as JSON, we still do, but we run a materialized view every 30 minutes to unnest that and turn it into a nice indexed materialized view in this sort of structure. It makes for, much easier querying. So JSON-B supports indexing as well. If I use the gin index, that's usually pretty fast. There are ways, within JSON-B, there are some new operators to get some faster indexes, but we've found for our cases it works pretty well. But say this is the containment operator. So over on the left, I've got a JSON blob, and I'm saying, well, does this JSON blob contain this JSON object? I can say, is there an instance of a key within this JSON object? Does the JSON blob on the left contain the key test? I can ask if it has all of the keys that I've declared. That's a Postgres text array on the right and a JSON blob on the left. I can also say, does it have at least one of these keys? I can also issue a query like this. I'm saying, hey, navigate down the JSON path and look at the test key and pull me out what that is equal to. In this case, it's pulled out the object where something is true. There's a lot more. I recommend reading the JSON documentation because, a lot of people have done benchmarks on it and it's really performant. This quote, basically EDB did some testing on it and they found that it was 2.1 times more faster than MongoDB for actually putting data in. Data inserts took 3 times longer in MongoDB. I'm not trying to rag on it, but between having your primary data store, which is usually Postgres and MySQL, and MongoDB over here, it absolutely scraps the need to have MongoDB. We also make heavy use of partial indexes. So using the cats table again, if I've inserted a lot of cats, some with pun names like Ricky Perveus, and we're running a site that connects people with cats that aren't jerks. Now, we might query this by select star from cats where is a jerk equals false. Say we get a lot of cats on the site, a few million. We'll create an index where it says is a jerk. What we've observed though is 2% of cats are not jerks. So by that we can say, well, 98% of our cats is a jerk index is wasted space. We rarely query for is a jerk is true. So essentially we're wasting space. What you can actually do with Postgres is implement a conditional index. So what I've done is create the same index, but I put the predicate on the end of where a jerk is false. What that actually means is, when we include this predicate, we're actually creating a very small index. In this case, we drop our index size by about 98% because there's data in there we don't really care about. We only want to index certain fields. We commonly use this where deleted at is null on a lot of our fields in our core database for our API setup. So we don't care about querying the email address of users who have been deleted. In some cases, we've dropped index sizes by 70, 80%. It's pretty damn cool. So concurrent web servers and concurrent application access, it's led to this case where there's a lot of race conditions out there. I do security research on the side, and I found about 5 big name sites who have race conditions just because they're using ORMs with no locks. There's a really common example. So, let's look at taking 100 whatever off a user who has a balance of 300. We could do this in Python. We could, select their balance from the accounts. We could check that they have an adequate balance. We could deduct it within the code and then update. This creates massive issues when we've got concurrent sessions accessing it. So say on the left, we select the balance. On the right, we select the balance. On the left, we update it, gets set to 200. On the right, we update it, it's 200. That's a really common problem. Postgres has some pretty cool ways of dealing with this. Most people on Stack Overflow say, well, just put in a begin commit statement that doesn't actually solve anything. We can either use row-level locking or we can use serializable locking. So let's look at the first way of, the suggestion of doing this all in one statement. We can say, well, update account, set the balance equals a balance minus 100, where the user ID equals, X, and balance is over 100. If we want to do any sort of inspection within our code, this is useless because, we can't actually pull data out. So what I personally do is row-level locking. So we've got our session on the left, we issue a begin. Over on our right, this could be a session that's accessing at the same time, it issues a begin. My first session will select from the accounts where the user ID equals 1, and it will add the for update statement on the end. What that does, that locks the row. If session 2 tries to access that row, it'll just wait indefinitely. The other transaction is still in process, it has to wait. Over on the left, we'll update the balance, set it to 200, and we'll issue a commit. That row is now unlocked. Over on the right, it's cleared. It can update the balance and set it to 200. Its select statement is now allowed to go through. It can update the balance and set it to whatever it was that we declared within the application logic. My slides are a bit wrong. Now it can issue a commit. That allows for basically atomic access. Postgres also has this feature of isolated, just this isolation level serializable. What that does, it uses some fancy math that I don't even know about to inspect which rows might be touched. So if our two sessions issue this isolation level serializable, over on the left we select for update. We just issue a normal select. My slides are once again wrong. The update won't do anything in this case, so you can leave it in there. Over on the right, we select it. Over on the left, we update. If we try and issue an update from the right-hand session, we're going to get an error saying could not serialize access due to this concurrent update. Over on the left, we'll commit, and it will all go through fine. What a lot of the libraries for this type of method, so within Ruby you've got SQL, and I'm not too sure if Django does it, they'll basically allow you to specify a number of attempts to rerun the transaction on the right, which did fail due to this concurrent update. Between row-level locking and this, one's basically just this explicit lock, and the other's this optimistic lock. It's hoping nothing else touches it in the process. Now, over on the right, normally a commit would be issued, and you'd get that error. In this case, a commit is turned into a rollback. So I'll try and speed this up. I've got a few more slides left. There's some other extensions. All of them have their own dragons. As you saw yesterday, you can do JavaScript within your Postgres using PLv8. There's trigram tools via the trigram extension, so you can do looking at sequences of letters, and they've got a few fancy operators for analyzing them. You've got partition management. So my first example where we had tables based on hour of the day, there's now an extension to do that for us. We did want to use that initially, but it didn't have all the features. It's had some really good improvement. You've got fuzzy string matching, you've got geo functions, international numbering standards, you can store trees, there's crypto, there's query statistics. There's just this whole mixed bag of things that you might want to do in your database. If someone else has already done the legwork and you get to take this code out of Python, that's a win in my book. On that topic, I was chatting to a few different people, and the question came up about doing web sessions in your database. I know there's been a bit of a trend to use Redis for this. I still stick with the database. It might impact performance, but you've got the ability to revoke these sessions. So if a user goes in, they can click, well, revoke this session because my machine's been compromised. You can get some analytics in your primary data store. As a security person, if I'm able to give my users a big button to hit with a list of the current sessions that are active on their account, that's a pretty cool feature to give. With Redis, you can't get that. So I say put web sessions in your database still. If it does impact performance, give it its own database, bump up the RAM. It should be an afterthought in terms of performance because you will be able to squeeze a fair bit out of Postgres. So I do have a wish list of shiny things that I want in Postgres because, thank you. Because it doesn't have everything. I absolutely adore Elasticsearch's, their search functionality. I can issue a search string, which is this really nice syntax to use. I can even submit that on behalf of the users, and it will show results. Some of the examples in the documentation that they take to concentration to look at, and there's just some really varied opinions around scaling. where to from one Postgres server? What are we going to do if we improve 10 times the size and we're still trying to store records of dynos launched on servers? We're not even thinking about that at the moment because it's kind of, it's not worth thinking about. It will just cause undue pain. So there's one place where I don't use Postgres, and that's Redis. I use Redis for distributed job queues, and that's basically because the libraries like Celery and Sidekick for Ruby, they support it. It's more of a convenience, really, because they've written it for Redis. That just means we have to boot a Redis instance. That's all there is to it. So I guess my takeaways from this would be that there's a cost with adding services and adding data pipes and moving data around. You run into dragons, it causes problems. Postgres does a pretty good job at things I throw at it. I said I've fallen into the trap before where premature optimization causes really poor design decisions. And the features complement each other. I said that you can use a triggered or a fresh or materialized view of some partition data just to shove in a cache. And who cares if it's 2 minutes out of date, if we don't need that. I'm also a big fan of the consistency that just having everything in Postgres provides. I know you can talk to Redis from within Postgres, but Redis doesn't have a way to roll back transactions. So over time, there is going to be an inconsistent state in my data, and I'm not ready to accept that. I don't know. With the trade-off being a small performance drop, I'm happy with that. And most of all, I have to give a shout out to the Postgres community because they have got an awesome roadmap. Their code is fantastic, and there's always improvements. 2 years ago, where I was using all these brand new services to now, I've developed a really fond appreciation for Postgres, so I'd recommend using it in place of a lot of tools that you use. So thanks for listening to the opinionated ranty talk, and we're going to have a bit of time for questions if anyone has any. Did anyone learn anything about Postgres that they didn't know existed? Okay, thank you. My job is done.
So anyone with questions, come on up.
Oh, God.
You took my job.
Okay.
Just use MongoDB. No. Sorry.
So you went over CTEs and also the recursive expression.
Yep.
In other less open source databases, you use the CTEs to do recursive queries.
Yep.
Can you do that in Postgres?
Yes. I didn't have enough slide room to do it, but I would chat to you about this repo afterwards because that'd be a really fun challenge, and I would love to put that in my repo.
Right. Okay.
So cool. Absolutely. Plus, we don't like paying for things. Open source is nice. It's free. It's really good.
Oh yeah.
Thank you. That was a brilliant talk.
Thank you.
Is there any way for Postgres to do essentially a live query where I do a select and then I start getting some mechanism where I can say what's changed since the last time this happened, or even like the listen notify, get notifications that, hey, there's some data that affects your query that might be spanning multiple tables through joins?
So like a streaming view?
Yeah.
Yeah. I know there are some extensions out there, and I know that a few companies are developing open source tools on Postgres where you can do streaming views. So basically subscribe to a view and it'll do your query and present you with results. So I know people are interested, but it's a really hard topic. There are levels of computer science I don't even want to touch where people are investigating this problem. If you don't mind stale data, there are definitely ways to automate it though. So, yeah.
Great talk. Thanks.
Thanks.
Another question about CTEs. Do you know if the query optimizer is able to get in and optimize, inside the CTE? Is that an optimization boundary, or does it?
I believe there are. It's not as optimized as say the table indexes or doing a materialized view with indexes.
Yeah.
But I know there is some forethought that's put into the planner to actually make these things pretty fast. With that verifications example I had, there's probably about 150,000 verifications in that table, and it's multiple milliseconds, so it does something on the back end. If you want to put that into the repo, I'd gladly do an analysis of how the planner is actually stepping through these things. So I think that'd be a really interesting one to investigate.
Cool, thanks.
No worries.
I've Googled for this in the past, but didn't find anything very good. Would you know where I can go to get the best info to migrate from MySQL to Postgres? Or is there any project within the Postgres community to help with that? Or?
To help with it? I know that there is I think the name might be taps, but it was basically a generic wrapper for databases to move data from one to the other. Can I talk to you after this, because I know that people at Heroku have worked on these things, so I'd love to get your details and work this one out.
Okay, thanks.
Yeah, thanks, Rhys. I just have a question about the new JSON-B data type you talked about.
Yep.
So if I got some tables that have the JSON data type, say I do them on 9.2,
Yep.
and we want to just alter the columns to change it to JSON-B,
Yep.
will Postgres do all the kind of optimizations that you'd expect to get out of JSON-B if we just want to?
If you want to change the type.
Yeah, so we just want to change the type from JSON to the new JSON-B, basically.
I mean, if you do a step migration, you could add another column to the table with the JSON-B data type and just do a coercion from the string to the JSON-B. You might have 2 or 3 minutes of, I guess, issues while you do the swing, but if you do it in small steps, it will re-optimize it into the actual binary format. So yeah, definitely doable. I could put that as an example in the repo as well. These are all great questions, so yeah.
Cool, thanks.
Cheers.
You mentioned there might be some extensions to help with the live query type scenario, and you also mentioned a great list of extensions in your talk.
Yep.
When I looked at the Postgres documentation, there was essentially a list of cryptic extension names and no description on it until you actually click on each link.
Yep.
Is there a good source of information on third-party Postgres contributed code?
Yeah, I know within the documentation, I mean, one easy way to do it is just to click the next button and see the name and then do the quick description of what it reads, but there's no real good, I guess, source for it. I know there is now a package manager for Postgres extensions, so that, I can talk to you about that afterwards as well. I can't.
What's it called?
Mainly because I can't remember the name of it. It's 4 letters in combination. I wouldn't want to get them wrong, but basically, that's the one. Thank you.
Sorry, what was that?
Thank you.
PGXN.
Okay. So there we go, being able to install extensions. So they might have some sort of directory, or they might be putting in a directory where you've got a nice list where it translates name to what it actually does.
Yep. Cool.
Thank you for
very
listening.
much, Rhys.